we already give you some understanding about the flame characteristic variations for jet diffusion flame by increasing the injection velocity of a given burner. Then you can see the flame length initially is almost linear increase with respect to the increased injection velocity. And later on, the flow structure, the flame structure will start to have some fluctuation on the tip of the diffusion flame. Later on, the laminar shape of diffusion flame will change to the turbulent flame, and the flame later on will detach from the base of the burner and stabilize at a certain distance away from the burner. And we call this as a so-called blow dip off. And if you try to increase the nozzle velocity furthermore, at the end of the flame lifetime, actually the diffusion flame will disappear. We call this as a blowout from the flow field, the jet flow field. In summary, as you go through the theoretical analysis, simply compare the flow time with for the flow convection and the diffusions, and you can estimate the flame length for laminar and the turbulent case. I just give you the simple relationship for the flame height with some function of the design parameter. For example, here, actually you can see this is the page 1.42 in your lecture notes. And here the flame height h is a proportion to the boiling flow rate, but inverse proportion to the mass diffusion coefficient. Then you can write it down as pi Rj. Rj is the radius of the jet pod square, and here this is the average injection velocity, and denominator represent the mass diffusion coefficient. Okay, and from this relation you can find out, and this is for the laminar case, actually the flame length is linear proportion to the injection velocity. Okay, in this estimation, basically we ignored the influence coming from the gravity, that is no buoyancy effect. And I already explained earlier, if you consider the buoyancy effect, actually the flame length variation with respect to the injection velocity will show you a slightly curved line, is a parabatic shape. But if you just consider, if you do not consider the gravity effect, the buoyancy effect, actually the flame length is a simply proportion, linearly proportion to the injection velocity, and we justify from experiment data nicely. And if you go to the turbulent case, you find out it is very interesting. The flame length is only proportion to the radius, the size of your burner. Okay, and which means if you have a larger size, then the turbulent flame will become larger. If you have a small one, then the small size of a burner, then the flame length of a turbulent jet flame will become smaller. And here, this plot gives you some systematic conclusion on the variation of the flame characteristics as we increase the injection velocity. Here, similar experimental result we already described, and here they just tell you how the structures you may have by changing the nozzle velocity. In the first portion, actually, they point out this is a laminar flame, and they show you a very nicely, smoothly flame shape, and the flame height actually is slightly curved, and the height is increased almost linear with respect to the nozzle velocity as we explained before. And I mentioned the turbulent fluctuation will start from the top, the tip of your diffusion flame, and propagate downward. And you can see there is the transition region to the flame appearance from laminar to the turbulent. Okay, when you have a turbulent flame structures, then those kinds of flame has strong fluctuation. Also, the they have some wrinkling and also have a strong fluctuation. But this plot did not show you the structures when the friend dip off. And there is they tell you there is a break envelope or break point. They tell you in some case the friend is already dip off. Okay, and they mention there is the highest friend height here. They say there is the envelope of the friend length, and in this region you can see as shown in the plot, the friend height is almost constant because in the experiment we just increased the injection velocity without change the diameter of your burner. Okay, and the lower part is basically coming from the experiment very earlier. And in this case, they use the city gas. City gas, friend, in that time, basically city gas is the propane as the major component, and they use one of 8-inch diameter nozzles, and this is the experiment for their friend height. And they actually those kinds of results are quite similar to our previous result by burning the methane fuel only. And there is the break point of the length to separate the large fluctuation of your friend appearance compared with the lower portion shows the laminar friend surface shape. And here there is the button of the port friend. That means that they start to have the friend dip off. Okay, and here they tell you friend separation begin here. Okay, and upper part of friend blow off, which means there is a region friends still stabilize on the port, and they show the propagation of turbulent friend structures from the from the tip of a diffusion friend to the base of the diffusion friend, and finally, and a friend will separate from the burner. That means we mentioned this is the so-called dip off. And if you continuously increase your injection velocity, then the flame will blow out. And here we try to summarize. This is a very interesting plot, and to try to let you know the different features for premise flame and diffusion flames, especially focus on flame stability. Okay, now how to bring these two stability limits for diffusion flame and premise flame together. This is a very interesting, and the result will bring you to the intermediate structure between the premise flame and the diffusion flame. Let's look at it. Okay, let's look at how to look at those kinds of variation of stability limits for these two flames. And here you can see from the plot, the horizontal axis basically is represents the percentage of butane. This is the experiment by burning the butane. Okay, and here we use the jet. We use the jet flow, and the vertical axis represent the velocity variation of your jet, which means along the vertical axis, actually you increase the injection velocity of your burner continuously. Okay, now look at this plot. Actually, we try to find a limiting condition for premise flame and for diffusion flame. The premise flame actually they exist here, right? Very close to the zero because there is the butane percentage means that they premise a certain amount of air. Okay, and you usually understand the survival, the stabilization of butane flame in a jet flow based on the so-called the Dean limit and the Rich limit. Between the Dean limit and the Rich limit, that is the flammability limit. In this range, you may have a flame stabilizer on the jet. Okay, and here you understand when you have a flame stabilizer on the port of your burner, and this flame will experience the two limits for given equilibrium ratio. Let me explain a little bit. And here in this plot, let me show you the first assumption, the first criterion here. The broken line tell you represent the inert atmosphere blow off. Okay, in this part actually they show you the stabilization limits for a jet impinging to the air environment. Remember, air environment, that means that you will have additional oxygen exist in the environment for the extra burning, for diffusion burning. If you the burning is under rich conditions, okay, you should remember this. But here, the broken line they mention, they tell you is the inert atmosphere. Inert atmosphere, that means that we eliminate all the burning, the downstream burning possible supported by the oxygen in the surrounding, right? Because the inert atmosphere, for example, you will think about they contains nitrogen only, then you do not have oxygen exist in the downstream side, then there is no possible to produce a diffusion flame in the downstream after the rich premise flame. Okay, now it is clearly to tell you in this condition, let's look at the region. There is the half moon region. You can see this is a half moon region, right? Okay, then we choose one of the percentage of butane, for example, here. Okay, by this line, you fix a butane concentration, for example, here, very close to the maximum value. Maybe in this condition, you may assume the mixing conditions is a slightly rich butane flame, right? Okay, and by a given percentage of butane mixed with air, the mixing ratio, then you will have a burning speed, right? And this burning speed allow you to stabilize your flame in the jet flow. Okay, for example, here at this point, okay, at this point, you can figure out at this point, and this flame at this point, that tell you the flame velocity, the flame speed is balanced with the flow velocity. Okay, the horizontal line represents the flow velocity, the injection velocity. They can stabilize here. Okay, at this point, you stabilize your butane premise flame at a certain on the ports, and the flame speed balance with the injection velocity. Now you can figure out if you try to reduce the injection velocity, how come? What is the conditions when you will experience when you now you have a point here, and at this point the flow velocity just balance with your flame velocity, right? Now you try to reduce injection velocity, which means the supply velocity becomes smaller than your flame, because the flame has its own flame speed and determined by the mixing ratio is fixed. But injection velocity reduced, that means that your flame will move closer to the burner, right? Because flame speed larger than the supply velocity. Then we call this where finally will close to your flame will flash back into your burner. Okay, then there is the boundary show you here. Initially, you have a point here somewhere in this in the region of this Harmon regions, and when you reduce the velocity, then you will reach to the so-called break the boundary for flashback. Okay, that is due to the flow velocity in decreased. Now, if you change your consideration, try to increase your velocity. Okay, now we move from the center point to the upper one. Velocity increase. When you have a larger injection velocity, that means that this local supply velocity will higher than the given flame speed. Then your flame will be pushed away from the burner, right? Push away from the burner. Finally, velocity is too large, and your flame speed cannot be balanced with the supply velocity to let your flame stabilize on your port. Then the flame will be so-called blow off, right? This is the purely think about the balance between the flame speed and the supply velocity for a given premise flame, which means when you have a concentration for given butane concentrations, and the stabilization of your butane jet premise flames will be bounded by the two boundary. One is the flashback, and the other one is blow off. Okay, I hope you understand the explanation on the stabilization of a given premise frame, the built-in frame. Okay, they are bounded by the flashback boundary, and also the upper bound will be blow off, depend on the injection velocity. If you have a smaller injection velocity, since for given mixing ratios, your frame speed is fixed. Okay, for example, I give you an example. If the frame speed is 30 centimeter per second, right, at this point, but injection velocity maybe for this point, now injection velocity around 45. Now you continuously reduce the 45 until maybe smaller than the 40, because we will find out there is the confluence, the position of your confluence depends on the alpha, the data. I think you already have this experience from the assignment 5 and also the midterm, right? Then if you reduce your injection velocity too much, then your frame will flash back. But if you increase your flow velocity, then you will push your confluence to have a longer frame length. Okay, but finally, it's too much. The injection velocity is too much, then you will push away your frame out of the stabilized point at the burner. Then we call this a so-called blow off. For given mixing ratio, even for lean or rich, and you will find out the possible stabilization of premise frame in your jet flows will be limited by this half moon region. Okay, and the lower bound shown here is a solid line. We mark it as a flashback. Okay, and the upper bound basically the left hand side represents a solid line, but right hand side will be shown by the broken line. As I mentioned, this broken line represents the difference in the inert atmosphere. Okay, you understand why we need to have this kinds of classification in this plot. When we identify the broken line represents there is no additional oxygen in the downstream of environment to give you a possibility to stabilize the diffusion frame, right? And here this is a rich region. This is a rich region, and here this is a lean region. Lean region. Actually, in the lean regions, the oxygens available or not in the surrounding is almost the same for the frame, because the lean frame means that you do not have excess fuel left in the downstream of your premise frame. Okay, then it is not necessary to think about oxygen available or not in the surrounding for lean case. But for rich case, if you consider oxygen inside in the atmosphere, then oxygen has a strong influence on the rich premise frame, because those oxygen will be used to support the burning of the excess fuel that in the downstream, right? Then that means that you produce a diffusion frame. Now you can think about, okay, we return to real conditions. The oxygen exists in the outer surrounding. Then for the rich case, now you may have, especially in this region, in this rich case, you may have diffusion frame exist accompanied with the rich premise frame. Okay, and as I explained earlier, when you have a diffusion frame in the downstream of your rich premise frame double frame structures, those diffusion frame will burn out the excess, the excess fuel, fuel depth in the downstream side. And this diffusion frame, actually, they will give you some support, because there becomes a hot temperature region, right? Have some heat will support the premise frame to be survive. Okay, and this additional support will give you the change of the upper boundary for the blow off. You can see for the rich one, this broken line will change to the solid line continuously, extend it. Okay, and this boundary for blow off regions, and to tell you in this case, for the link case, the blow-off is simply governed by the is influenced by the balance of the French speed or premise French speed with the flow velocity. But for the rich case, for the rich condition, actually this the extent of blow-off is not just controlled by the balance of French speed and with the flow velocity. They have additional influence that coming from the diffusion frame. And this outer diffusion frame give you to extend the limit of blow-off to a further experience higher injection velocity. Okay, and this solid line and the dotted line, the broken line, has a different feature based on the oxygen available in the downstream side. Okay, now this is very clear to tell you the stability limit for a premise frame exists in a jet flow. Okay, now we already have some explanation on this part. Now we move to the right-hand side. When you go to the 100% butane, at these conditions, they tell you that now we have a purely butane diffusion frame, right? Okay, now simply you can see now starting from the injection velocity equal to 0, you find out you can figure because now you just have show you the velocity variation and also the variation on butane percent. But here you can have some experience from our flow, the frame appearance influenced by injection velocity. Then you can see as you increase the flow velocity along a vertical line, then you will find out, you will figure out, try to imagine the frame height is continuous, almost linear increase, right? Continuous increase, continuous. At certain point, they start to have a fluctuation from the top of a diffusion frame, and those fluctuations will propagate from the top to the base of a diffusion frame, and finally you can find out the frame base cannot stabilize on the port, then the frame dip off. Okay, then you can see we reach to the boundary of this so-called dip, the boundary for the dip off at this point. Okay, this is a dip off. And if you continue increase velocity further, and actually the frame will stabilize at a certain point in your flow. That means the dip frame. Okay, here they mentioned there is a dip frame. Now you continue to increase the velocity. Now finally you will end up with a so-called blowout. The diffusion frame cannot be stabilized in your flow. Okay. Now for the purely butane diffusion frame, they tell you around the increase in the flow velocity, you can experience a linear, the stabilized laminar diffusion frame. Then the frame dip off, and finally will blow out. Okay, it is quite clear to give you all the possible stabilization features for a jet butane frame. But now we try to think about, there is two region, right? One is a so-called premise frame we already identified very nicely, and then the premise frame means that you will mix your fuel with air completely from the beginning. That is pre-mixed in. Now, then the other boundary we call this is a pure fuel without air premixtions. Now these two ends, we clearly understand those kinds of stability limits based on the for the premise frame is bounded by the flashback and blow off, but for the diffusion frame is bounded by the dip off and also the blow out. Okay, before we jump to the intermediate region between these two these two limits, we need to explain a little bit for another line. Here, for example, if you start from a dip frame already dip off at certain points in your jet flow, now you try to bring it back. How to bring it back to the burner base? You try to reduce the velocity, right? Then you try to reduce velocity. When you try to reduce velocity, surprisingly, when you reduce to the points at the dip off conditions, actually the frame cannot come back on stabilize on the port unless your velocity decrease to a certain value lower than the velocity for the dip off. For example, here Now at this point, the lower boundary here, the flame drop back to your burner. Okay, this is a big difference between the injection velocity to produce the dip off and the flow velocity to end up with a drawback. They are not the same velocity because those kinds of flow structures, the process for changing the flow structure is different. One is from the low velocity to the high velocity. The other one is the high velocity to the low velocity. You try to enhance the turbulent intensity or decrease the turbulent intensity. They cannot reach at the same point. Okay, this is the one point I need to mention. Here, actually, I write down the sentence here to tell you the high velocity turbulent jet mixed with the surrounding air, and at some points about the burner ring, the flame attach itself to the flow and maintain itself in a broad region of turbulent mixed flow. This tells you when you increase the injection velocity, the flame will dip up and stabilize at a certain point of your jet and survive for a certain time as you increase the injection velocity. Okay, and they say they can maintain itself in a broad region of the turbulent mixed flow, which means they can experience a range of the increasing injection velocity. But they tell you the important thing is, as the flow velocity is increasing from some velocity, dip up will occur along the top edge of the cross hatch region. Here, this is a cross hatch region. Okay, when you increase the flow velocity across the cross hatch regions, then flame dip off. But as the flow velocity to this dip off is decreased, the flame will drop back to the ring at the lower edge of the cross hatch, at the cross hatch, the lower edge of the cross hatch region. Okay, which means the velocities, flow velocity required for dip off is different from the flow velocity required for drawback. Okay, they are different, and those is limited by this cross hatch region. Okay. Now you clearly understand those kinds of behavior. Okay, the left-hand side tell you the feature stabilization for flame stabilization for premise flame, and as 100% butane give you the stabilization feature for purely diffusion flame. But in the middle, okay, this is an interesting part and bring us to further to learn the combustion catalyst, therefore so-called the partially diffusion flame. Okay, we say in the left-hand side we can have the purely premise flame. Okay, and but usually it is very hard to say the purely premise flame because if you need to think of the pure diffusion, pure premise flame is basically defined by the premise flame in the inert environment, okay, without additional diffusion flame. But for the premise flame here, if you burn those premise flame in the oxygen environment, you may have a double flame. Actually, the diffusion flame already influence in a rich condition for premise flame. Okay, but mainly in this region, from the lean limit and the rich limit, actually the flame catalysis is governed by premise flame majorly. Okay, but for the diffusion flame, actually, we just debating about the pure diffusion flame based on the butane concentration equal to 100%. Between this rich limit and the pure diffusion flame, then we call this a so-called the partially diffusion flame. Okay, because in this range, you understand inside of the jets, you have a certain amount of oxygen premixed with fuel. Okay, between this, you can find out those stabilization limit has a connection together. You can figure out here. The blowout regions, this nice actually is connected continuously to the line of the dip off. Okay, okay, there's a connections, and the blowout line actually do not have a. They just has a attach point with the line for the drawback. They cannot go through the premise flame regions. But in this part, we call this as belong to the partial diffusion flame. Actually, even up to now, people do not spend too much time to study the flame structure in this area, but we still can present some interesting result because they tell you some combustion characteristic. They just exist in the region between the purely premix flame and the purely diffusion flame. Later on, I will tell you how they give you some idea to think about actually this in this region is a really structures, right? Because you in a turbulent flow structures, you may not purely so-called premix flame or purely so-called diffusion flame. When they have a double, when they have a region in these two region boundary, you try to think about how they how the meaning of premixness and the fuel and the oxygen separated completely. I mean the diffusion control. Then we try to bring it together for the nature subjects.